Now let us talk about total angular momentum. And before moving on with this video, I request all of you to share these videos, and I request all of you to like the videos and subscribe the channel, and so that these videos can reach to the people who have some state of interest uh, in learning science, in learning physics. So, what we have to discuss now is that we would like to talk about the angular momentum and how we correlate the things. We have atom, it has nucleus, and it has electrons, and each electron in an atom has certain orbital angular momentum. So each electron has angular momentum. And angular momentum, and it has spin angular momentum. It has spin angular momentum. And we have symbolic presentation for angular orbital angular momentum as L, and for spin we have S, and they are vectors. And and now what we are trying to tell is that this orbital angular momentum and spin angular momentum, what it does, it contributes to the total angular momentum. It contributes to total angular momentum. And this total angular momentum is the vector J. And and if we consider an atom whose total angular momentum is provided by single electron, and atoms of the elements in the periodic table, if we go to the first column, where we have sodium, potassium, and all of those elements, they have one electron in their outer orbit. And uh, and these one electron in their orbit, atoms like we have hydrogen, and we have lithium, we have sodium, and so on and so forth. And they have single electron in their outermost shells. And 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 what is important here is that Pauli's exclusion principle, it has to ensure that the total angular momentum and magnetic moment of a closed shell, total total angular momentum and and magnetic moment and magnetic moment and magnetic moment for a closed shell has to be equal to zero. And in the same category of, if we have the ions who have lost their electrons, and they have one electron in their outermost shell. And in these atoms and ions, the outer electron's total angular momentum is basically the vector sum of it is it's basically the vector sum of L and S. So if I have to write down this, if I have to write down this total angular momentum, what should I do is, I have J, and this J is L plus S. And like angular momentum, this J is also quantized. And it's quantized both in magnitude as well as direction. That should be borne in mind. And the magnitude of this quantum, this total angular momentum J, is given by under root of J times J plus 1 times H cross. And this J, the particular J is particular L plus particular S. Now this S can be plus minus. Now, if I assume that L is equal to 0, J will have a single value, and J will have a value equal to 1 by 2. If I take the Z component of J in Z direction, what should I write? I should write Jz the way I was doing for angular momentum, orbital angular momentum. That will be mj h cross, where this mj is it's minus j, then minus j plus 1, and so on and so forth to j. So what we have is the simultaneous. What is important is that we have simultaneous quantization of J, L, and S. They all have to be quantized. They can have only certain specific relative orientations. This is the general conclusion that we have, what we are trying to understand here. And in case of one electron atom, there are only two relative orientations possible. And what's that? One relative orientation corresponds to, what will that correspond? That will correspond to L plus S. So there are only two possibilities for atoms who have one electron in their outermost shell. And what is that? You can have J equal to L plus S, and you can have J equal to L minus S. Now, in case of J equal to L plus S, here certainly this J is greater than L, and the overall J, and in this case the overall J is less than L. So how can we draw it vectorially to have at least a feel of what I'm trying to say? Suppose we have L given by this vector, and we have in the same order we have S. Then this closing vector is my J. And this is my case where J is L plus S. And this L plus S will certainly be 3 by 2 in this case. And what is another possible orientation is, suppose this is L and this is S. And this is J. Now in this case, J is L minus S. So that will be 1 minus 1 by 2, that will be 1 by 2. Here it is 1 plus 1 by 2, so it will give us 3 by 2. So the two ways in which L and S can be added to form J, when we have L equal to 1 and S equal to 1 by 2. Now plus 1 by 2 is for this kind of vectorial presentation where you have the same order for angular momentum and the spin angular momentum, and the resultant of these two vectors is given by the third vector directed opposite to the order of L and S. So this way we can have an idea of coupling that we are trying to talk about. Now this angular momentum we have is that now what we have is the angular momentum S, and we have spin angular momentum S, and orbital angular momentum vector L. And what they do is they interact as as we have discussed that in the previous video. They interact magnetically. And if there is no magnetic field, for no magnetic field, I mean external magnetic field, there's no external magnetic field, the total angular momentum J will be conserved. J is conserved. And it is conserved in magnitude as well as direction. So it has conserved magnitude and it has conserved direction. And effect of the internal torques that we have. So there is a consistent interaction between orbital angular momentum and spin angular momentum. And what it does, it causes some internal torques. It causes some internal torques, and this internal torque causes precession. It causes precession of L and S around the direction of their resultant J. But if we apply, now if there is external magnetic field, now when we apply external magnetic field, and then what happens, this J presses about the direction of magnetic field, while L and S continue pressing about J. L and S continue pressing about J, and what J does, it presses about the direction of B. And this precession of J on B, the precession of total angular momentum J on B, is what gives rise to anomalous Zeeman effect. So this becomes the basic root cause, the pressing of the external magnetic field on the total angular momentum. And we understand that this total angular momentum has a relation with orbital angular momentum and spin magnetic moment and spin angular momentum. And this J can be correlated with those set of values for magnetic moment of the electron. And that's how we will have what's called as G splitting factor. When this G splitting factor comes in action in the equation, we are able to understand why we have large number of lines in anomalous Zeeman effect when we are applying the weak magnetic field to the system. And this is because of the different orientations of J, the total angular momentum vector, and which is slightly different with slightly different energies in the presence of magnetic field. So this G splits up into many parts because of slightly different energies in different directions. So this was the idea. This was the core idea about the total angular momentum vector.